Alright, 7.4, the remainder and factor theorem objectives. Students will be able to evaluate functions using synthetic substitution and determine whether a binomial is a factor of a polynomial by using synthetic substitution. So, it says use synthetic division to divide this by x plus 1. Alright, well, remember synthetic division, we take the opposite of whatever's in here. So if this is a plus 1, we're going to write a little negative 1, put that in our corner. Then we're going to write all the coefficients in descending order. So the first one is 1, then 4, then 1 again, and then negative 6. Draw a line underneath, and there's where our remainder goes. Bring down the 1. 1 times negative 1 is negative 1. 4 plus negative 1 is 3. Negative 1 times 3 is negative 3. 1 and negative 3 is negative 2. And negative 1 times negative 2 is positive 2, which negative 6 and positive 2 makes negative 4. Okay. Now, what I want to point out is, here we found, we used negative 1 in synthetic division. Now what I would like for you guys to do is plug in negative 1 to this function. Go ahead and do that and see what you get for f of negative 1. You can pause the video because I'm going to put the answer up in just a second. Okay, so when I worked all this out, plugging it all in, I end up with negative 1, 4, negative 1, negative 6. All my negatives, negative 1, negative 1, negative 6, if I add that up, 1 and 1 is 2, plus 6 is negative 8. So 4 minus 8 is negative 4. So this is the interesting thing here. Look, when I use synthetic division to divide with negative 1, I ended up with negative 4. And using the same function, when I plugged in negative 1, I ended up with negative 4. Coincidence? I think not. So we have the situation here where if we use synthetic division, the remainder will actually equal the same thing here. So what I want you guys to do is find p of negative 1 by not by plugging it in here, but instead by using what we're going to call synthetic substitution. It's just using synthetic division and figuring out what the remainder is, just like I did up here. So go ahead and try that, see what the remainder is when you divide this thing synthetically using negative 1. And I'm willing to bet that would be the same thing that p of negative 1 equals. So go ahead and try that. Again, you should pause the video, and I'll put the answer up in just a second. Okay. Now, if you forgot that you needed to have every term there, meaning you need to have the x there, so there's really, like, you can imagine there being really a 0x right there. If you forgot about that term, you would have gotten the wrong answer. But if you remember to plug in that 0 there and put everything in the right order, once you use synthetic division, you should end up with negative 69. And that is what p of negative 1 is. It's negative 69. And so this is just kind of a quick way to evaluate a function. In fact, you can do several functions. You could set up a table and just synthetically divide by several factors to figure out what the solutions are. It's a quick way to generate a table. And that is actually what the remainder theorem is. It says the remainder is the value of the function when evaluated at that factor using synthetic division. So, on this next one, what I want you to do is, again, use synthetic division to divide this polynomial by x minus 4. So I'm going to set it up with you guys. Make sure you set it up right. Remember that the 4, we do the opposite of negative 4, so we would do positive 4. And then write all the coefficients. And we don't have anything missing, so this should work out real nice. And go ahead and do the rest on your own. I'm going to pause the video and put the answer up in just a second. Okay, so I did all the synthetic division, filled it all out, and I got a remainder of 0. That means that x minus 4 is actually a factor of this. And then we get this polynomial left over. Remember, I don't give this one an x, give it 1x, give it an x squared, give it an x cubed. And I get a new polynomial that is also a factor of our original polynomial. The polynomial you got by dividing out the factor x minus 4 is called a, I'm just going to write it below so I have enough room, a depressed polynomial. This is useful because now we could actually find all of the factors by factoring this thing out as well. And we'll see how to do that later. When the remainder is 0, like the problem we just did, then that binomial is a factor of the original polynomial. Like I said, this is known as the factor theorem. Factor theorem. The binomial x minus a is a factor of the polynomial f of x if and only f of a, so when you plug in a for the function, it should kick back a 0, meaning it's a 0 of the function. Alright, well how else could we find some zeros? Well, we could graph this thing. But what I wanted to show you here is that we can actually use synthetic substitution to generate this table relatively quickly. So let me show you how we would do that. I'm going to kind of create a synthetic division table. Here's what it's going to look like. Here's all my possible values for x. Over here are all my coefficients. 1, -3, -6, +8. And down the line here, I'm going to put in all the values that I want to test for x. Now I know that you guys have learned how to create a table on your calculators, but we're going to just show you how you could do it relatively easy without a calculator. So let's just do a few numbers here to start off. So let's do like -3, -2, -1, and 0. It does require a little bit of mental math, but I have faith in you guys. So we make this table. Remember, this is where our remainders are here. And remember, our remainders are actually what our f of x values will be. So for example, the remainder I get here will be my f of -3. So let's give it a shot. Remember, when I synthetically divide, I just bring down the first term, so this is just a 1. It's going to be a 1 in all of them. -3 times 1 is -3. So -3 plus this -3 makes -6. -3 times -6 is +18, and +18 plus this -6 is 12. -3 times 12 is -36, and -36 and +8 make -28. So there's my f of x value. Let's keep going. -2 times -2 times 1 is -2. Add it to this number up here, makes -5. -2 times -5 makes +10. +10 and -6 makes 4. -2 times 4 makes -8. -8 and 8 makes 0. Interesting. Let's keep going. -1 times 1 is -1. Add it to -3, you get -4. -1 times -4 is +4. Add it to -6, you get -2. -1 times -2 is +2. Add it to 8, you get 10. Okay, one more. We take 0, add it to 1, or multiply it times 1, sorry. We get 0. 0 and -3 is -3. Alright, 0 times -3 is 0. Add it to -6, you got it, -6. 0 times -6 is 0. Add 0 to 8 and you get, that's right, 8. Now, if you wanted to, you could check this process against the table that this would generate in your calculator, and you'd find that all these values are the same as what you would get when you plug in -3, -2, -1, and 0. So this is just a nice, simple, quick way to evaluate a function without actually having to plug it in the long way and just figure it all out. It's pretty neat. The rest I actually already filled in using my calculator, so I'm just going to give you guys that information. After 8, we get another 0, and then a -8, then a -10, then another 0, and then a positive 28. Okay, now that we have a table here, I'm going to let you guys graph this, and then I'll come back with the correct graph and show you guys how to do the rest of this problem. You should pause the video now. Okay, once we graph this thing, we see that we have 3 zeros. One at -2, one at 1, and one at +4. -2, 1, and 4. So these are actually the factors of this function. We did the same thing with quadratics. So we could write a factored form of this function by breaking it up into a bunch of little parts. We know that x equals -2 is one of the zeros, that x equals 1 is one of the zeros, and that x equals 4 is one of the zeros. So if I get all these equations equal to 0, it'll end up looking like x plus 2 equals 0, x minus 1 equals 0, and x minus 4 equals 0. Well, that means that we could write it all as a factored form as x plus 2 times x minus 1 times x minus 4. And that equals the same g of x as up here. If you wanted to test it, you can synthetically or use long division to divide out one of these factors and see what you're left with. You'd be left with the other two factors. So just kind of a neat thing that works out there. Just know that the zeros give you the factors, but it's the opposite. So if you have a 0 at -2, your factor is going to be x plus 2. Or at +1, your factor is going to be x minus 1, and so on. So we've been able to rewrite this function using the zeros. Okay, example number 4 says, show that x plus 3 is a factor of x cubed plus 6x squared minus x minus 30. Then find the remaining factors of the polynomial. Okay, so first, we're going to show that this is a factor by using synthetic division. So remember, we're going to do the opposite, so we put in a -3, and then we have a 1, a 6, a -1, and a -30. Go ahead and do synthetic division here real quick, and if it is indeed a factor, this will end up being a 0. -3 times 1 is -3. 6 at -3 is just 3. -3 times 3 is -9. -1 and -9 is -10. And -3 times -10 is positive 30. And there we go. 30 and -30 make 0. So that means that x plus 3 is indeed a factor. And the depressed polynomial we get after we divide out x plus 3 is going to be x squared plus 3x minus 10. So we could rewrite this whole polynomial as x plus 3 times x squared plus 3x minus 10. Alright, now what did they say? They said then find the remaining factors of the polynomial. So now we're going to say, can we factor this anymore? And we can. This is a 3, by the way. So what we're going to do here is we're going to do our little magic x. Put the -10 on top, 3 on bottom. We need something that multiplies up to -10, adds up to 3. How about a 2 and a 5? And how about we make the 2 the negative? -2 times 5 is -10. 5 plus -2 is 3. So we could say we already had this factor of x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we can use these two factors, x plus 3 and x minus 2. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this, we can use these two factors, x minus 2 and x plus 3. And now we know that this and x plus 5. And now we have factored this thing down all the way to our 3 factors. And if we really wanted to, we could even figure out what the zeros are of this function. It would be -3, +2, and -5. For the last question, it's a summary. I want you guys to try it on your own. It says the volume of a rectangular prism is given as this function. One side of the prism is given by this factor. Find the expressions that represent the missing measurements. This problem, even though it's kind of a word problem, and it's dealing with a rectangular prism, is actually the same as this problem above. You're going to divide out x minus 4 from this thing, and then factor out the trinomial that you have left. Same way we just did it. So go ahead and give that a try, and I'll put the answers up in just a second. Okay, if you do this one right, I'm just going to fill in the answers down at the bottom so you can check and see if you did it right. But if you do it right, you should end up with x minus 4, of course, that was the original one, and then also x minus 1 and x plus 8. All right, see you guys on the next video.